circuit diagram is minus VEE RP, all of the things. So this current IE, which is going to be going through this RE, this should be constant. That will be equal to IE1 plus IE2. This resistor RE, that is equal to IE. This IE should be constant, and this is also called as tail current. So we can put it as IT also. Tail current, the tail current is IT. Now I will replace this section of the circuit with another circuit in order to make that IE constant. So just connect that circuit with a transistor. This is our third transistor. And the base of transistor is connected to this resistor. And from the emitter side, we have another resistor. This is R2, this is R1. This is your Q3, third transistor. This is also your current. Current in here will be I3. IE. This IE. Third emitter of the third transistor, IE3. Okay, the current which is flowing through the emitter of third transistor. So this IE3, this will be equal to VE3 minus VEE divided by RE. So consider here, this is your emitter, this point you will be having VE3. Potential at this emitter, third transistor's emitter leg, this leg. Okay. So consider this, this is having potential of VE3. This means VE3 means potential at the emitter of third transistor. That is at this point. Okay. And here we have potential which is minus VE, this point also minus VE. So if you take these two potentials, VE3 and minus VE, take the difference between these two, that is potential difference, divided by this resistor, between that, that will be the current which is flowing through that. Okay. So the circuit is like this. I have a resistor here. So this is your VE3. This is your minus VEE. This is RE. So take the potential across these two points, which is VE3 minus VEE. Difference between those potential. Divided by RE will be your current which is flowing through this. This is your IE. So this will give VE3 plus VEE divided by R. Another equation which is for VBE, total voltage of this third transistor. So that will be given by VB3 minus VE3. I'm talking about this VB is base emitter voltage of third transistor. That means this one. Okay, this one. If you consider VBE will be nothing but potential at VB minus potential at VE. So that is VB, potential between base and emitter. So VB minus VE will come for third transistor. So it will come as VB3 minus VE3. Third transistor. Now applying Kirchhoff's current law, so you have to consider this one. So actually, you have to redraw this circuit. Redraw that part only. So we get here R2. Here you have that potential at base VB R1 is connected to minus V. Talking about this one. Okay. So here this is VB base voltage for the third transistor. This will be. So I'm just I just redraw this section, input section of this transistor here. So applying Kirchhoff's law in this circuit, Kirchhoff's current law, this circuit will give VB3. You can put this is 3 because it is third transistor. So VB3. So VB3 minus 0. Consider this resistor. So here we have VB3. Here this is grounded. So VBE minus this potential is 0. Divided by R2 will be the current flowing through this resistor. Divided by R2. That is the current is flowing through this. Okay. Then consider this resistor. I have to add this plus VB3 minus VE divided by R1. So this should be equal to 0. Considering that this as a closed loop. Okay, so if you consider this as junction, otherwise you can apply like this. This is your I1. Okay, I1 means the current which is flowing through this, and consider this as your I2. Okay, so at this junction you can say that current whatever which is coming will be equal to current which is leaving. So you can also write it like VB3 minus 0 by R2 equal to VB3 minus VEB R. That is also possible. So from this, we can write VB3 equal to minus R2 times VEB divided by R1 plus R. So VB3 is common here in both terms. So VB3 you take as common, and then we will be having 1 by R2 plus um, here it will come. You can do that VB3 1 by R2 plus VB3 have taken outside. So how this will come? This term 1 by R1 plus VE by R, right? So this will come on plus VEE by R. This term we need one VBE. Here one VB3 will come, right? Or you simplify this, okay? So that you get this expression. So first you have to take this VEE by R1 that side into right hand side. So that it will come VB3 by R2 plus VB3 by R1 equal to VEE by R1. Then take VEE VB3 as common. So it will come VB3 into 1 by R2 plus 1 by R1 is equal to VEE minus VE by R. Now you can simplify this. Just cross multiply and take the other side. You get like this. So this will come R1 R2 divided by R1 plus R2 times R1. From here one R1 will get cancelled. R2 by R1 plus R2. This is VB. So that is expression for VB3. So now my VBE3 here also 3 because it is base emitter voltage of third one. So I can put here also 3. This will be equal to VB3 from this expression. So VB3 will be minus R2 VEE divided by R1 plus R2 in this expression. VBE I am calculating. VBE equal to VBE will be equal to VB3 minus VE3. This minus VE3. You can put equation number if you need. Put here 1, 2, substituting 2 in 1. So now my VE3 will be equal to minus VBE3 minus R2 VEE by R1 plus R. Just take this VE3, this one to the other side and multiply with the negative. Okay, so this is my VE3. Now IE3 will be, what is IE3? This expression. So you can put this as some IE3 I had to calculate. So in IE3 I had to substitute VE3. Okay. And this is third, 3 in A, IE3 equal to minus R2 VEE by 1 plus R minus VBE 3 plus this one VEE, right? Plus VEE divided by R. So this expression is coming from expression A. Okay, first equation that we wrote. Just substitute there what is the value of VE. You will get like this. Now since IE3 is almost equal to IC3, implies IC3 equal to IE1 plus IE2 is equal to 2 IE1. Considering that two emitter currents are equal, so IC3 will be 2 IE1. Remember it is coming because we are having IE1 here, IE1 here, and IE2 here. So if you add these two, you will get IE3. Sorry, this one is IE or IT. So this is also will be equal to that current which is reaching at this collector end of the transistor. Okay, so that is IC3. This one is also IC3 because the same current will be reaching at the collector end of the third transistor. So this is IC3. So this IC3 will be equal to IE1 plus IE2 is coming from these two transistors. And if these transistors are identical, IE1 will be equal to IE2. That will give you this as 2 IE1. Or you can also put 2 IE2. Because IE1 will be equal to IE2. If these two transistors are identical, these two current will be same. So that will give me IC3. That is the current which is coming from these two through this tail to the collector end of third transistor. That is IC. So that will be equal to I1 plus I2. That is nothing but 2 I1. That's what I put here. Now if you put uh, this one IE3. So IC3 is this. So IE3 will be also the same because IE3 is almost equal to IC3. For transistor IE will be almost equal to IC. So that will give me IE3, sorry, 2 times IE3 will be equal to Sorry, this one is here I am substituting IE3 will be equal to IC3. So IC3 will be equal to 2 times IE1. So IE3 will be 2 times IE1. So 2 times IE1 will be equal to minus R2 VEE divided by R1 plus R2 minus VBE 3 plus VEE divided by R. Now what will be this IE1? This IE1 I can write this 2 you take this 2 to the denominator. Sorry. So here it will become 2R. IE1 will be equal to all these terms divided by 2R. Just put that. Okay. So if you check this one I3 here, this is IE3. IE3 is the emitter current for the third transistor. This one. Okay. So this current will be constant here because all the terms VEE is constant. R2 R1 we can fix. VBE is the base emitter voltage of transistor, that is also constant. VE is again constant, R is constant. So by setting these parameters, we'll get constant IE3. Similarly, you can get constant IE. So the tail current, which was going through here for the first circuit, this one, this is nothing but your 2 IE1 or 2 IE2. This IE1 is constant, so 2 IE1 also will be constant. That current will be flowing through this because of that additional transistor and this configuration. By using this circuit, we are making that IE3 or IE1, IE2 constant. So this current should be constant. In order to make this current constant, we are having this additional circuit, the tail of differential amplifier. Okay, so that's what we have. Then here, from here we can see IE1 equal to R2 VEE by R1 plus R2. All these are constant. These things are also constant. So this IE1 will be also constant. Current will be constant. Only it will only depends on your R1 R2 values and VE. So by using that circuit which we just explained, using this circuit we can make that emitter current or tail current as constant. And it is essential for differential amplifier that this tail current should be constant. Also, in order to avoid the temperature fluctuation because of temperature there will be some minority carriers, etc. In order to avoid this temperature, if the temperature vary, then there will be charge minority carriers variation. So in order to avoid that, we will also connect one diode here. That is not that much important, but just remember that this is the diode which is connected because sometimes we will connect one diode like this before that resistor R1. Okay. In order to avoid the effect of temperature, if temperature varies, temperature increase, minority carriers will come and that will change the current. In order to avoid that, we will also connect one diode here. Just to open parameters. So in operational amplifier, the first stage of the operational amplifier is the differential amplifier. So let me discuss with that. Open parameters. So in op-amp parameters, first one for ideal case, an ideal op-amp exhibit following characteristics. So first one, infinite voltage gain. This is for ideal op-amp case. The gain of that op-amp operational amplifier will be infinite. Okay. And second property is, we will explain this later. Infinite input impedance all these are for ideal case, okay? For an ideal op-amp. So infinite input impedance. Third one, zero output impedance. And also zero output voltage when input is zero. And fifth one, infinite bandwidth, which means that all frequencies can be amplified. Number 6, infinite CMRR, common mode rejection ratio, CMRR. If there is any common mode between those two legs, that will be rejected from amplification. So how much that ability? That ability will be infinity for ideal case. So it will completely remove that common voltage. The last one is infinite slew rate. Slew rate. Slew rate means output variation. So input slew rate means output changes simultaneously with the input change. If you change input, how fast the output will change. That is the slew rate. So in the case of ideal case, it will be infinite, which means that if you change input simultaneously, output will change very quickly. So slew rate means if you are changing the input, how the output is going to change, when the output is going to change in time. So if it is happening very quickly, then its slew rate will be high. For ideal case, it will be infinite, which means that if you change input at the same time, the output will change. Yeah? But in practical case, we have some problems here. Ideal case, this is the condition. And in consider that symbol. This is the op-amp diagram. We can say this is the equivalent circuit of the op-amp. The, the differential amplifier and all other circuit will be inside this portion. This is your plus VCC. This is the biasing voltage plus VCC and minus VCC. We will be having the output, which is from the output. This is your inverting terminal. This is your non-inverting terminal. This is your V1. This is your V2. These are input terminals. We already discussed when we did that differential amplifier. One will act as inverting, other one will act as non-inverting. So this is your inverting terminal. When you put this signal, input signal in this terminal, output will be out of phase with 180 degree. If it is non-inverting, then phase will be the same. And inside we can represent it like a resistor here. And this output is taken from resistor, which is this is your R output. This is your R input. So here R input will be infinite. Okay. This will be infinite for ideal case. Input impedance is infinite, and our output will be 0 for ideal case. Okay. So this is an equivalent circuit of equivalent circuit of open without feedback. Okay. So without feedback. So there is no connection from input to output. If connection is there from input to output, that is feedback. So without feedback, connection will be like this. Equivalent circuit will be like this. And the V output will be equal to A times VID, that is difference of input voltages. That will be A times V1 minus V2 in this case. That we already discussed when we did that differential amplifier. The difference between two input will be amplified. So the output phase depends if you are connecting both terminal. Okay, if both signal is applied, if signal applied both input terminal, so that the phase phase means phase of output signal. Okay, phase of output signal will be determined by the magnitudes of V1 and V2. You can write it in your own words. Actually, you are having V1 minus V2 here. So depending on your V1 and V2 value, your phase will be, because when we are applying both signal. Okay, V1 and V2, we apply V1 and V2 here, both terminal. So if V1 is larger, then this will become positive. Okay, so there is no phase change. If V1 is small, then this will become negative. So there will be a phase change here. So if both are active, magnitude of V1 and V2 determines what is the phase of the output. And if you draw that output, you get like this. So this is your VID, difference voltage. It is straight line. Okay, this one is straight line. And when it reaches a certain voltage, it will become like this. This is your V saturation plus V saturation. This is your minus V saturation. So this is your output voltage. This axis is output voltage. This is your VID. So actually, in ideal case, this V out will be very high. This is not the exact magnitude. It should come like much more steeper. Okay. In reality, it will come like this, very close to this one. It will be very high. So that V out will go to infinity, or the gain will be infinity for ideal case. Okay, but we never get infinite gain because we are applying plus VCC here, minus VCC here. Maximum voltage that you will get will be this one, plus VCC or minus VCC. More than that, you will not get. So when you say that infinite gain for ideal case, okay, so that never will happen. This will not happen in real case. In reality, practical amplifiers, this will not happen. We will not get infinite gain because we are applying plus VCC and minus VCC here. That biasing voltage, maximum output that we will get is plus VCC and minus VCC. So when you are having output which is more than plus VCC or minus VCC, this will become saturated. Output will become saturated. So this plus V saturation will be equal to plus VCC. This one will be equal to minus VCC. So once your output reaches plus VCC or minus VCC, your output will become saturated. Even if you increase that difference voltage, it will become saturated. More than this, no. Okay. Now this open loop op-amp configuration can be used in different amplifying circuit that we will discuss in next. So this is some basics. Now we will discuss in the next class. We will discuss all these terms easily. Okay. For ideal case first, then for practical amplification.